to recording. Hi, everyone. Welcome to the Monday seminars. Super happy this week to have François Renard joining us from Oslo. I think people have been here before. This is a seminar series that started during COVID and made us realize that it's an incredible opportunity if we're lucky enough to get great speakers, and we have been. Our normal mode of operation is to ask you to mute yourself so that we don't hear background noise. But if it's okay with François, typically people are, if you have a point of clarification, you want to ask a quick question during the talk, go ahead and unmute and ask it. And otherwise, one of the nice things it's been is we've had a great long discussion and question and answer period at the end of each one of these talks. So we'll plan to do that today. We'll really encourage everyone to participate in that discussion. So especially for early career people, make some notes of questions you have and raise your hand at the end and join in. The formal part of the introduction happens by email. So I hope you read it. Because for me right now, I just want to turn things over to François, thank him for being here, and look forward to hearing his talk.
Thank you, Chris, and thank you for organizing this great seminar series, because I have followed many of them, and I really enjoyed it. So we'll talk today about a journey I made since 2019 on, as an experimentalist, how to use machine learning to interpret experimental data. And this talk could not have been done without key contributors. So John Icon, I see, is in the audience. That's the machine learning expert of our group. Yehuda Ben-Zion, with whom we discussed a lot on what we see on small scales in the lab, how can we interpret that in the field. Benoît Cordonnier did most of the experiments I will show you. Nilima Kandula is a PhD student who is now a postdoc at the Australian National University, and we work on this topic. Joachim Mathisen is a professor of physics in Copenhagen, also an expert in computational physics. And Jessica McBeck did her postdoc with us, and she now got a permanent position as professor in Trondheim. And perhaps the way it started for me is this big picture of what you see on the right side is how can we predict the distance to failure or the proximity to failure of geological objects. It could be a piece of rock that will fall in a landslide or a rock fall. It could be an earthquake. That's a picture of a meter scale displacement in a lower crust fault outcropping in Western Norway. Or it could be these two glaciers that collapsed in 2017. And that could be observed through satellite imaging. All these processes, there is a question of how does it start? And what I will show you is that all these processes, at least in the lab, they start with some damage that accumulate in a rock volume before it fails. And for me, what has been inspirational to use machine learning was this conference, and I'm happy that Paul Johnson, you are here because you were one of the organizers, with Greg Beroza and Daniel Trugman. That was a conference in 2019 in Santa Fe, New Mexico, where I discovered the world of machine learning. And my talk today will be my journey from 2019 to now, from someone who did not know anything about machine learning and would try to learn something, because I got great colleagues who helped me on this. So as you know, the view of an earthquake or any kind of other rock failure process is some accumulation of energy, here for an earthquake at a crustal scale, then a rupture that propagates, leading to a fast displacement, and sometimes an after sleep or some relaxation after the major event. So that's what we teach to our students, is that there are faults and earthquakes occur on fault. Let's go now to Southern California, where the faults here are the black lines. That's an article from Ross et al. In 2019. And all the seismicity, that's all these points with the color coding corresponding to depth. And in this area, the main earthquake occur on faults, but tiny earthquake occur off fault in a large volume around the main faults. So there is an alternative view of fault system, is that earthquake occur on the fault, but there is also some lot of activity in the surrounding volume in 3D, sometimes quite away from the fault. So the reality is that there are faults, but there is also some distributed deformation around the fault in some volume, which can be of hundreds of meters to kilometers around the fault. So that's a cartoon of a normal fault system in the North Sea. And this article from Faulkner et al., where they could identify the fault core and the damage zone that has been measured away from the fault core. So here, over a distance of more than 100 meters. And this damage zone is measured by the number of microfractures or the density of the microfracture in the rock. So that's the same conceptual view with a fault core and some volume around that accumulate some damage. So let's have a simplistic view of what happens before one of these major failures. There is a system which can contain a fault or not, in which some precursory inelastic strain will accumulate, leading to a system size failure. And here, this block could be a landslide, it could be a glacier, it could be a fault, it could be an object 1 by 1 centimeter by 1 centimeter, or it could be a crystal block. And one of the difficulty with this large-scale geophysical ruptures is that they start with, at a very small scale, one atom will start to move, push another atom, propagate across the scale to the scale of minerals, heterogeneity, and the big earthquake will propagate over distance of several hundred kilometers over the crust. If we want to start at the nanometer scale, we can do molecular simulations. We can reproduce fracture, friction at this scale. It's, however, difficult to propagate across scales to upscale from this scale to a scale larger than several micrometers. On the other scale, from kilometer to 1,000 kilometers, what we do, we solve differential equations that we validate by observations. That's the big earthquake simulators. But what we put in these differential equations will come from observations and experiments we do at this scale. And that's where comes the laboratory earthquakes. They are done at scale of millimeter to meters, sometimes even tens of meters. And they are used to identify processes and test theories, like die latency, fracture mechanics, nucleation of the rupture, which is still a big unknown, rupture velocity, frictional framework, and they are used also to measure parameters, fracture energy, rock strength, effect of fluids, is it a weakening or a strengthening effect? And what is measured here in numerical simulation validated by experiments and observation, that what will be used at the upper scale to upscale earthquake simulations. So today my talk will be mainly on taking small rock samples, centimeter scale, apply some stress, vertical and confining, and measuring some strain. So this has been done in the rock physics community for almost 100 years now, even more than 100 years. What has been done in the past 50 years is to record the deformation either microscopically, so measuring the shortening of the sample, and that's what is represented on this curve, is the axial stress that is increased on the rock sample, and the shortening measured. So the sample is shortened until this point C, where the sample is failing on a big fault, and then there is slip on the fault. And to measure the internal strain, acoustic emission sensors are glued on the rock core. And for example, in the group of at USGS of Deck Faulkner published this paper almost 40 years ago now, of the location of acoustic emissions as a fault form in this system. However, this group identified that this acoustic emission, they represent only a tiny amount of the strain. So they record perhaps less than 1% of the strain in the system, saying, in other words, that more than 90% of the strain is aseismic, doesn't produce any seismic signal. And this has been demonstrated more recently by this paper by Cartwright Taylor et al., who coupled 3D X-ray imaging of sandstone in which a fault developed. So that's the stress strain curve. And acoustic emission recorded, and they concluded that acoustic emission only record a tiny fraction of the deformation. And this is possible now to see inside rock samples through a new technique. Well, the technique is not new. It's called X-ray imaging. It has been developed for medical imaging in the 1970s, and it has been improved over the years. And now it's possible to see a rock sample like this piece of Fontainebleau sandstone. So it's a rock cylinder, and the color coding on the blue is the porosity, the white is the grains, and you see that there is a fault that form. And here it's a piece of Carrara marble, so 5 millimeter times 1 centimeter. So that's the view of the sample bulging and faulting from the outside, and that's the view inside the sample of all these little microfractures that are these little brownish elements that will form and then localize into a fault. So to use this technique, we use a big X-ray source. It's called a cyclotron that produces X-rays. X-rays, they have a wavelength in the angstrom sub-nanometer range. So there is almost no limit in spatial resolution of what you can image. There is a limit of data, how much data you can produce. But because of very short wavelengths, we can image rock samples with spatial resolution of sub-micrometers. And many groups have started to build this kind of apparatus that is installed on a cyclotron. So there is a rock sample inside, and this apparatus produces condition of temperature, pressure of several kilometer depths. And they produce the data for the movies I've just shown you in the previous slide. So this apparatus, there are many groups. We built one 8 years ago. There is this one built by the group in Edinburgh. There is a rotary shear apparatus built by Nicola Tisato. I think he was in the audience. And in the US, there is this network, in situ studies of rock deformation, that coordinate all these activities of neutron and X-ray imaging on big instruments. And probably that will lead to more and more of this machine being built in the near future. So most of my talk today will be on using this data, 3D data, time-lapse, so an evolution of a system, leading to localization of fracture until system size failure. And I show you one experiment here of a piece of rock. So the grayscale here, that's the minerals. The blue part, that's the damage, microfracture accumulated. There is the axial shortening in red, the volumetric strain in blue, or the radial strain. And this sample is loaded. So I put a more circle for the geologist here. So this sample is loaded by increasing the axial loading. So that's why we have different circles, and each circle corresponds to one of these 3D volume. And here, that's the sample at 99.95% of the stress at failure, so just before it fails. On this sample, when 0.1 megapascal is added to the curve here, the sample will fail. And when it fails, you will see it at the end of the movie, the sample collapse. And when it collapses by producing these two conjugated faults. That's the sample here that has been failed. So with this data, we have a 3D image of a rock sample every 6.5 micrometer in 3D as a function of time. And the question we will ask is, if we have an image of a rock sample like that, where more or less we know all the damage in 3D, can we predict the distance to failure or the proximity to failure? So intuitively, a sample with more damage will be closer to failure. But how much? Each experiment is between 1 and 3 terabytes. I think now we have more than 40 in 8 years of experiment on the cyclotron. And I will mainly show you results of experiment on 8 samples that we have studied over the years. 8 samples time, let's say 2, it's 16 terabytes, and 16 terabytes, how to dig into this data, that's how we had this idea to use machine learning. So we have this 4-dimensional data of damage. what we will do, we will characterize the parameter that control microfracture growth and the proximity to failure. So we are not the only one who did that. Other groups did that in another context. It's a context of a shear experiment or friction experiment. And it started with a paper by Rouet-le-Duc using experimental data from the group of Chris Mahone. And then Corby, Johnson, Wang et al. So there were more and more papers on this topic, where the idea is to use stick slip experiment where the shear stress is measured as a function of time. And each stress drop here corresponds to an earthquake, a laboratory earthquake. And on this experiment also, the acoustic emissions are recorded. So that's the acoustic emission. And the idea of this, all this machine learning approach is that if we know this curve at every point, because the horizontal axis is time, we can predict what is the time to failure. So 0, it means the point here, there is an earthquake. Then the time to failure increase, and then it will decrease again through this linear step function. And the question is, can we, using acoustic data, predict this curve? If I have well understood these papers, but I think I did. And that's what is predicted using machine learning. So entering this data, it's possible to reproduce this data. And there have been even a Kaggle competition to find the best fit on this system. So I use, in the Oslo group, we use the same kind of approach, except that instead of having this kind of data, so stress as a function of time and acoustic emission, we had 3D imaging of samples as a function of time. And it's a bit like in a video game. You know, in a video game, you start level 1, and level 1, you start easy. So we started with basic statistics. Then we went to level 2, unsupervised learning. We use XGBoost. And then I will finish with level 3, which is the deep learning. And I will show you that at every step, for us, it was a learning approach to machine learning. But at every step, we learn something, and we, at the end, we get results which I think made sense and show that a deep learning model have learned something about rock mechanics from this data. So let's start with the level 1 of our game. So we started with this kind of data, so a series of experiments. So we had 4 experiments, 2 on Carrara marble, 1 on granite, 1 on monzonite. We use these rocks because these rocks, at the beginning, they don't have any porosity. So when we image the porosity as a function of time, it corresponds to the amount of damage that accumulates. And what we want to do in the system, we want to predict for each fracture, so each of these blue objects, what is controlling their growth. Why does a fracture grow? What is the parameter? So we perform a series of experiments. We have between 50 to 100 of these 3D scans as the sample approach failure. And then one of the students, Nilima, she wrote a code that tracked each of these blue fracture and was tracking how each of the fracture was growing when the sample was loading. Knowing that some fracture, they will grow, but if a fracture grows, a nearby fracture could close. Then, because we can define the characteristic of each fracture, we develop a logistic regression. I will come back to that. And we use a recursive feature elimination. And we track at the end, what we want to understand is which parameter will control that every single of these fracture will grow or not. So now we have rock samples in which we have thousands of fractures. And the fracture, we characterize them by 14 parameters. So there are 3 parameters that correspond to the length of the fracture. So we fit each fracture with an ellipsoid, and we use the length of this ellipsoid or the dimension in the 3 directions. So that's what we call the eigenvalues, sorry. Minimum, intermediate, and maximum. Then we have also the orientation of these 3 axes. So if the long axis is vertical, the fracture is parallel to the sigma 1, to the loading. we have three parameters which correspond to the shape: anisotropy, elongation, and volume. Volume is the volume of the fracture. Elongation, it's if the fracture is more like a cigar or a penny shape. And anisotropy, if it's a penny shape that is really a circular penny or an elongated penny in one direction. And then we look also at the distance between fractures. So for each fracture, we have 9 plus 5, 14 characteristics. So we have a big Excel spreadsheet where for each fracture, we have all these 14 parameters. And for each fracture, we know if the fracture is growing or not. And then we fit logistic regression. So I assume that all of you have been to university sometime. And when you are at university, you are a student, and then you go to a course. And then you decide how much effort should I put in my course to pass it. And the logistic regression is this function. Each point here is one student, one different student. And the outcome of passing a course is either you fail, so that's 0, or you pass, it's 1. And the horizontal axis, that's the number of hours a student has been studying this course. So that's the student who fail, the student who pass. So there is not a big surprise if you spend more time studying. In average, you pass the course. And this function is just a sigmoid function around these points. That's called a logistic regression. So instead of having a student, we have a fracture. So what point will be a fracture? 0, the fracture does not grow. 1, the fracture grows. And our studying is not the number of hours. It will be the 14 features. So we can build these things in 14 dimensions. So we use the 14 features. We fit a logistic function. We classify into positive and negative outcomes. So the fracture is growing. And then we use the machine learning technique. So we randomize the data to have an exact number of fracture that the same number of fracture that grow and fracture that do not grow. We split between 80% training, 20% training. Testing, we run 50 models of with different data. And then we analyze the data with by their importance. So we have the 14 features, and we just cumulate between the samples. What we see is the features that are important, that this one, that's the one with the black circle. So that's the minimum distance to fracture. So if a fracture is close to another one, it will tend to grow more. That's also the orientation of the fracture. If a fracture is vertical, it will tend to grow more than if it is horizontal. That's these three values, that's the dimension of the fractures, including the maximum length. So that's in the fracture, the longest direction in the fracture is an important parameter. And the parameter that is not important is the elongation. And then come a surprise for us. So first, let's take all the fracture and look at the elongation of the fracture as a function of stress. So the sample will fail here. For the fracture that grow and the fracture that do not grow. What we see is that the growing and non-growing fracture, more or less, the elongation is the same. So if we come back here, elongation is not a very important parameter that controls fracture growth. But now let's look at this one. So this one is the length of a fracture, so the longest axis. The black one, that's the fracture that are not growing. They have a length of around 40 micrometers. And the fracture that are growing are the fracture that have a smaller length. And for those who have studied fracture mechanics, it's the opposite of fracture mechanics. If a fracture is longer, it will grow more. It will be easier to grow than if it is shorter. So more or less, this result contradicts fracture mechanics and the Griffith criteria, at least at this scale. Does it make sense? And the answer is, in this case, is yes, because the rock is this rock. It's a Carrara marble, so we took this sample after the experiment, we sliced it and make a thin section. And that's what the sample looked like. So it's quite damaged. All the black, it's porosity, it's crack. But for example, here, that's a grain, a Carrara marble grain, and that's a fracture. And if we start to map the grains and the fracture, what we see that most of the fractures, they stop at the grain boundaries. So in this system, the grain boundaries are pinning. There is a strong pinning of the fractures. And that's explained this effect, is that after some distance, the fracture will stop growing and will meet a grain boundary. So that was an unexpected result. In other words, that the length of the fracture control is growth. It's not a big surprise, but in this case, it's the shortest fracture that do not grow. So after doing a logistic regression, which was, for me, it was very close to statistics when we did that. Let's go to level 2. So level 2 is gradient boosting machine learning. So again, we start with experiments, the same set of experiments. Here we have 8 instead of 4. So we have all this circle, it's a 3D volume, a bit like that. And we measure the distance to failure through this parameter. When it is 0, the sample is failing. And when it is 1, it's far from failure. And this image, that's 2D slice in the sample. So every little black object, it's a fracture. And the fractures are growing until the sample fails. And what we want to predict here is the distance to failure. So this distance for a given sample, like this one, can we predict how far it is to failure? What is the proximity to failure? Is delta equal 0.5, 0.3, 0.01? So we did the same. We extracted all the fracture here. And instead of using 14 features, we use 40. And we even added feature 41, which was a random number between 0 and 1. So for each fracture now, we have 40 numbers. So the numbers are the 14 as before, the length, the orientation, but we have also the proportion, the 25% largest fracture, 50% largest fracture, some percentile of this fracture. That's how we reach 40. And then we measure the distance to failure. So we have a R2 value between the predicted and the true distance to failure of 0.5, 0.6. It's not great, but it's still a positive, strong positive correlation between the predicted and the result. And we use these two measures, which are used in the machine community, learning community. So one is called the feature importance, and the other one is called the Shapley additive explanations. And this feature, these two metrics, they tell us what is the importance of the 40 features in predicting the distance, the proximity to failure. So first, if we look at feature number 41, which is a random number, you see that's the one with almost the lowest importance. So if we add a random number, we cannot predict the distance to failure, which is reassuring somehow. Now, if we put all the 41 features, we have a R square of 0.56. But what we can do also is select some features. So if we select the feature that have the 4 features that have the most importance, so that's the angle of the fracture, the opening, the spacing between fracture and the anisotropy, so it's not very far from the elongation in this case. In average, we have R square of 0.4, 0.44. We can also use the 3 best features, only 2 features, only 1 feature. When we have only 1 feature, then the R2 start to decrease below 0.2, so the correlation between the prediction and the true distance to failure becomes very weak. But if we look at these 4 parameters, so the orientation of the fracture, the aperture, the spacing, what it says that the orientation of the fracture, it's part of the Moore-Coulomb criterion on how fracture will propagate until the system will fail. The fracture, aperture, and the anisotropy, so the ratio between these 2 axes, that's under the stress intensity factor, so that's fracture mechanics. And the distance between fracture, so how fracture interact, that's a measurement of how the strain energy is distributed in the volume. So the 4 most important factors here that can predict the distance to failure, that's a combination of Moore-Coulomb, fracture mechanics, and strain energy density. And if we combine them together, that's how elastic strain energy is dissipated in the system as damage is growing until system size failure.
François, sorry, it's Chris. Can you remind us what you're comparing to produce that that R squared term?
So for each sample here, I know this distance. So I call that the true value.
I see. Okay, so it's proximity.
Then I predict this distance and I plot the true value. I make a plot where X is the true value and Y is the predicted. And I calculate a correlation and an R square of this.
Gotcha. Thank you.
Okay. So if R square was equal to 1, it means that I would predict fully. If it's 0, it's not very good. Between 0.5 to 1, it's a positive correlation. So there is correlation. So let's go now to the level 3, it's the deep learning. So the difference between what I presented so far is that there was here someone who decided to extract features from the 3D images to say, okay, let's make hard work to extract fractures, to calculate the parameters. And then when we have the feature, we can fill some unsupervised learning model, XGBoost, for example, to calculate the proximity to failure. So the last part of my talk is how to use this data to feed a deep learning. So a deep learning, you remove this stage. You remove the user. You just start with images like that. And what you want to predict is this distance to failure. So we started with 8 experiments. That's the same 8 as before. That's a stress strain curve. So the shortening of the sample as a function of the loading. And the last point here on the right side of each plot is when the sample is failing. So during all this increase of stress, the sample is accumulating damage until it fails. For some samples, we have a lot of data. For some samples, we have only 3 or 4 of these data. And what we want to predict is this distance. So say it in another word, in other words, if we have a rock sample here in which we can image all the fractures. So we start with a volume like that. So that's a rock sample where there is a 1 when there is a fracture and 0 when there is no fractures. And let's take 2 slices in this 3D volume, and that's what we get. So in this sample, the axial loading is vertical, and that's the fractures, the black dots or the black lines in 2 perpendicular slices. As you see, this system is very sparse. We have a lot of 0 and a very few ones when there is a fracture. So the goal is to feed a deep learning model with this image and to make a model that will predict the proximity to failure. So from 8 samples and several 3D scans, we produce 40,000 2D images of this kind. And for each image, we know the distance, the proximity to failure. So we know this distance because we know that this 3D sample has been taken at some distance. Then we developed 3 deep learning models. In the first learning model, we just use 1 image per sample. So instead of using 2 images, we use 1. In the second model, we use 2 images for each sample. And in the third model, we use also 2 images, but we train differently. So the way we do this, we start with 2D images, so 40,000 2D images. The 2D images are 600 by 250 pixels, so 250 by 600. We have 40,000 of them. And we start to convolute them with filters, 64 by 64s. And then we enter this machine learning, deep learning. And at the end, what we predict is this delta. So we predict this. So we enter 1 or 2 images in the model, and we try to predict the value of delta. So I will try to explain this one. This one, that's the main result. So I will try to explain it slowly. So we have all this 3D image from which we extract 2D image, and we feed the deep learning model to calculate this distance. This axis here, it's the distance here minus the prediction to the square with the square root. So that's a root, mean square error. That's an error. If all the points were at 0, it means that the prediction would be perfect. Then we have a null model. So that's the great point. A null model is just to say that we randomly select a distance to failure for all these points. So we take an image and we say randomly the distance to failure is this value. And we have a value here about 0.08 because what we did, we selected only the sample that were in the last 20% of the distance to failure. And the reason is that before 20% to failure, there is no damage, so we cannot see anything. So the null model is here. That's the gray plot. Then we have a model which is based on the density of fracture. So we just calculate the density of fracture and try to predict the distance to failure based on the density. That's these little blue diamonds. And by the way, the 8 samples are here. Then we train the model with only 1 image. That's CNN single, or with 2 images. So with 2 images, it's performing better. And this one, which is performing very nice, but that's not a surprise, is correspond to how we train the model. We can train the model either by using 7 samples and predict number 8. So it means that we feed the model with 7 samples and we predict number 8. And that's the blue point here. Or we train the model with the 8 samples with 80% of the 40,000 image, and we predict the 20% left by the deep learning. And the prediction is much better because the 8 samples are in the model from the beginning. So by the way, what does this mean? This residual means? It means that we predict the distance to failure within 5%. And for one experimentalist, it means also that when you do experiment, if you do 10 times the same experiment, you get 10 times the same result. And when you are within 3-4%, you consider that your results are somehow experimental results are robust. So that we reach this 4% here, it's for me as an experimentalist, it's within close to the experimental error. So it's not that a big surprise, in fact. So that's the input is the images, and that's the stress strain curve. That's what is predicted. So that would be the stress strain curves of the 8 samples. So they look like a stress strain curve, in fact. Another way to look also at this data is to, now we have a model, is to say, okay, instead of feeding real data, let's feed the model with synthetic data. So we created images like that, 250 by 60 with pixels. These pixels are randomly spread on the image. It's called a speckle noise. And we enter this image into the deep learning model and ask what is the distance to failure. And we produce thousands of images with a different density of fractures. So that's the fracture density of this image, and that's the distance to failure. So 0 would be close to failure. So it's not a surprise if the density of fracture in the synthetic image increases, the distance to failure decreases. So fracture density has an effect. It's just that it's not sufficient to explain the distance to failure. You need to have more information, which is probably due to both the orientation, how the fracture are distributed, to predict the distance to failure. So that's the residual, the predicted distance here minus the true distance, where we use only the density of fracture in our real data, and it's quite spread. And when we use the full image, like this one, and when we use the full image, the residual is much lower. So it means that we predict the distance to failure here, the proximity to failure, much better in a deep learning model where it is fed with a complicated image like that, compared to an image to feeding the model with only the density of fractures. And then we continue this little exercise of let's feed now the model with image like that contains stripes. And we play with two parameters, the angle of the stripe. So let's assume that the vertical would correspond to the loading in our experiment. So the angle of the stripes and the distance between the stripes. So the distance here corresponds to the density. If delta W is larger, the density of stripe is smaller. And now we ask the deep learning model trained on our experimental data, we ask the following question. What is the distance of failure of an image like that, or the proximity to failure of an image like that as a function of theta, so the angle between 0 and 90 degrees. So 90 degrees, it will be horizontal fractures. 0, it will be a vertical stripe. And for different value of delta W, so for different densities of fractures. So first, let's compare the density. So the density is the position of this curve. What we see that more or less the fracture density does not have a strong effect. Oh, and by the way, that's again the same number as here. That's the difference. That's the distance to failure here, this number. So when it is close to 0, it means that a synthetic image like that would be recognized if it was a rock as close to failure. So first, the density does not change much. But what is interesting is that there is a minimum here of all the curves for stripes orientation between 10 and 30 degrees. And what is 10 and 30 degrees in this context? It's the Moore-Coulomb criteria applied to faults, so that's Anderson theory of faulting. So it means that this deep learning model, coming from image like this one on the left to the image, finds that the optimal angle of faulting is between 10 to 30 degrees. So without learning rock mechanics, it finds rock mechanics. It's not a very new result because Anderson theory of faulting is 1905. But for me, I found interesting that this way we train data, at least something came out that makes sense. So we can look also at when we use filters to convolute with the image, which filter have the strongly activation. So this filter is 64 by 64 grayscale images. And some of them don't have a structure, but this one on the top right has a structure which looks like the stripes that I've shown here. So it means that on images like the two image of fracture here, this filter is activated, and that's so I don't know yet if it is what control the fact that Anderson theory of faulting appears in this deep learning, but at least that's intriguing. That's a correlation, which is not a causality between a filter here and the theory of faulting. So to conclude, that was my journey to machine learning. I started with statistical logistic regression method, and step by step I learned. I think it was driven, as I said, by two things. It was this conference I attended in 2019 in Santa Fe, and then this massive amount of data, several terabytes per samples, and how to dig that. These tools were useful to make sense of this data. So we started with supervised learning, then to deep learning. Deep learning predict the distance to failure from images of fractures in rocks in our experiments. The distance to failure is better predicted than with images than only with fracture density. So it means that in a fracture network, the size, the distance between fractures, so the 3D organization or the 2D organization of the fracture has a stronger effect than the density itself. And then this deep learning model has found an optimal fault angles in the range 5 to 30 degrees, which is in agreement with the Anderson theory of faulting. And I will leave you with this last slide, is that when we do experiments and we have artists working nearby to us, we can start to interact. So that's some piece of art that has been produced by an artist working with us. And some of it even made the cover of Physics Today, so 3 years ago. I thank you for your attention.
Really cool. Thank you very much, François. I'll invite people to, yeah, what an interesting talk. Okay, now, while François is catching his breath for a second, we can maybe do what John has done. You raise your hand. There's a reaction button at the bottom of your screen. Yeah, it's useful to put us in order. And we would like to encourage as many people as possible to raise their hand and participate in the discussion, questions, and other things like that. So John already has his hand raised. Please go ahead, John.
Hi, François. That was very good. I especially liked the part with Joachim because I hadn't seen that before. One question that I had is that because you talk about how you go from statistics to deep learning, and so one question that I had is kind of like two points. The first is, do you see a time dependency of your residuals as you get closer to failure? So does the model get better the closer you get to failure? Yeah, so slide 34.
34, is it this one? No, 34.
I think it's,
yeah, but this one, this
okay,
one is, I think it would answer.
Yeah.
So that's approaching failure. And the spread here would be the residual.
Yeah, okay.
So I didn't do the exercise, but visually it's not clear.
Yeah. Yeah, because that's true. It doesn't seem like there's a clear delineation. Yeah, you can't really tell from these plots.
That's a good point, yeah.
But the follow-up question I have, and that's it's kind of maybe it's a more philosophical question. It's when you're predicting the time to failure, you're kind of you're looking into the future. And you're saying, well, I know it'll fail at some time, and actually I know when it'll fail, as opposed to predicting how the stress between this time step and the next time step. And so I guess my question is how well does this uncover the actual time evolution of the system? since you're looking all the way in, or I mean, there's a lot of questions here, but
I'm not sure I understand. What is the question?
well, so if you know how much the total amount of stress is to break the rock, right?
Yeah.
And you know that because you ran the experiment all the way through until it breaks. Well, if what then your model kind of knows future time steps. So if you look at this plot on the left, each point on it is a time step, right? Because it's one more strain on the sample. And so if you're looking at the difference between like I don't know, the one that's labeled and the end versus the one that's labeled and the second, the one that comes immediately after it, those are two very different values. And one is kind of like more of like the dynamical process of what goes from 0 to failure. And the other is kind of like it's like jumping ahead into the future and saying, well, what's going to take me to failure from this point in time? And I think those two questions are very different. And so, because it's like what predicts the next step in the time evolution of the system and what predicts the failure of the system, because actually that time evolution is important to the failure, but it's like it's not captured by the model. I don't know if I'm making a question or if I'm just like
I think I can understand part of it. I will try to understand that because we did something different, and I think you were part of this one, no?
yes, yes, but it's been a while.
Yeah. So with this X-ray tomography data, what we can do is a 3D image correlation. So we can correlate images one after each other and look everywhere in the sample the local strain, shear, dilation, contraction. So that would be a dream for, I don't know, geodesy people. Imagine that you're a geodesist and you have an INSAR image, and you have the INSAR image every 100 meters below the surface until 20 kilometer depth. So you would have like a 3D strain view. So that's what this kind of thing does. And that's what we did here, is that we divided the stress strain curve in 10 different, and we look at the time succession. It was, one issue is that to go from one to the other, when you have very little strain, there is very little information that change in the system. So looking at this data incrementally, the accuracy first was, that's the accuracy, was not great, let's say it like that, in our system. So probably what you say would be it would be possible to do. We just need better data, more data, and probably even higher spatial resolution to look at it incrementally instead of to look at it globally. But that's a good point, yes.
John, you want to follow up? You're happy?
No, I think Renzo answered my question. There's like I have lots of questions about this, Francois. So we can talk outside of
So
this.
you are in Oslo?
Yeah.
Great. Paul Johnson, go ahead.
Thanks, Chris. François, super interesting. I mean, what you're doing is quite unique, and the fact that you're using that to try to predict failure is fabulous. Here's one or two questions, if you don't mind. The first is something we tried, Chris Johnson, Kun Wang, and myself tried, was using transformer models to actually predict the future. When you do time to failure, you're predicting a regression curve. So it's a contemporaneous prediction of a regression curve of time to failure. And what we did with the transformer models was try to predict future steps into the future. And it's just a suggestion of something you might try if you haven't already. I presume you haven't tried that, but it might be interesting to try that.
Yeah, that's a great idea, because that's exactly it's. So first, we didn't do it just because it would be for us level 4, you see. We did level 1, level 2, level 3. Now that would be another step. And the other reason, it's a bit like the John questions. In your system, in the experiments, at least if you refer to the experiments, you have several cycles. So the
Right.
system repeats more or less.
Right.
For me, it doesn't repeat. It's when it's broken.
Right.
So the only way to repeat is to do more experiments. And the cost of one experiment is $20,000. So you can imagine that I cannot do too many of them. So I will have to find a way to do this. But that would be exactly what you said is from one of these 3D image, can I predict the next one?
Right.
Be
I mean,
the-
you may have to turn to simulation. I think this is something everybody in geoscience faces at one point or another, that you just don't have sufficient data
Mm.
to train supervised models. So point well taken. One other question for you is, are you simultaneously recording acoustic emission?
Not on this one. It will come probably in 1 or 2 years.
Okay.
It's just that there is one machine we can do it, is this one so far, and there has been one paper, which has been this one. I will try, I am building the next machine. It will take a bit of time, where
Right,
I will have 3D and acoustic emission.
So obviously, I think we know where you're going, which is to say you'll have multimodal data that you can use for predicting. So that'll be really interesting. So I have other questions, but I'm going to get off right now and let other people. Thank you so much, François. Fabulous work.
Paul, thanks a lot. And you can always chime back in. Yeah, it's really nice to see you, Patrick. I have to say, I've taken inspiration from many things you've done over the years. So nice to see you here. And yeah, please go ahead with your question.
Thank you very much. Thank you, François. It's really impressive. I did not quite follow your recent work, and I'm really, really impressed. I was trying to imagine how you can go from the lab to the field, because it's not just a problem of change of scale, but also in the lab, some of your parameters, I think they have their relevance because you know the stress field, for instance, the orientation. Trying to go outside the lab, then this is some kind of thing you will lose. So did you try to understand what could be the impact of the loss of relevance of some parameters when you don't master everything like in the lab?
So there is, so in the field, when at a large scale, we do also numerical simulation at a large scale. We have a different approach, but just for example, adding a zone which is damaged around the fault and see how this damaged zone will control the final rupture. That's an important step, which is now done by many people, because the way the energy is transferred from the elastic strain energy from the bulk volume to the fault when it breaks, it will depend on this damage zone. So having some damage that will accumulate until it breaks, that could be one way to look at, to use our data to upscale. So here, what shows the experiments is that there is a complexity where part of the 3D volume will contribute to the final rupture. And that's the concept to put in this differential equation. It's an extra parameter, a damage zone with some properties that could evolve or not before failure. So that's how I think that what I bring here could be used.
Okay. Thank you.
Great. And as we go to Nicola Isato, I would like to re-encourage everyone, especially young, early career people. Raise your hand, and I'll be happy to let you jump the line and ask your question even before Alex shoot now.
Thank you, Chris. Yeah, thank you, François. Incredible presentation. Really, really amazing stuff. So I would like to ask you if you discover why shorter fracture were growing and the longer were not. First of all, so if you can give us a bit more insight on that, And then the other question, somebody already kind of asked and responded. I mean, the image is the image, but if you know also the state of stress and all the acoustic emissions emitted at that moment, you might be able to constrain even more, right?
Yeah.
You're not putting that right now, right?
So I don't know if you have been working on Carrara marble.
Yeah,
Did
a
you?
bit.
A bit. So this rock is incredible because it can accumulate a lot of damage before it fails.
Yeah.
And that's what happened in this rock.
Yeah.
You have some grains and lot of fractures. It corresponds to the opening inside the grain. And when these two fractures have opened and they reach the grain boundary in yellow, they stop because there is a large energy to cross and break the other grain.
Sure.
So it means that this fracture will stop and it will cost less energy to open another fracture in another grain somewhere else. So for example, here you have an example. We have the same fracture that crossed two grains, but that's quite exceptional. So that's the reason. And probably it comes also from the strong anisotropy of calcite, because that's calcite grains, and calcite, they have this cleavage that are very weak. So once the cleavage breaks, it breaks, but breaking perpendicular to the cleavage, the fracture energy is much larger.
So it is completely due to the boundaries between grains then?
Yeah.
So you have seen this only on Carrara marble or also on other rocks?
Yeah, because on other rocks, I would have the same. I would have the same thing on other rocks. I would have that the maximum length of the fracture, for example, on the granite, the maximum length of the fracture is an important parameter.
Sure.
But if I was doing this plot, I would have the long fracture here growing and the short fracture there not growing.
Mm-hmm. Thank you. Yeah.
And the second question for acoustic emission, I agree it would be interesting, but just also there is an important point which was raised by David Lochner, then Georg Dresen also showed that, is that the acoustic emission, they record a tiny, tiny fraction of the strain in a rock physics experiment. So meaning that with the X-rays, I can get 100% of the local strain inside the sample, more or less. But the acoustic emission, they will record only a tiny fraction of it, which is on the order of 1%.
Yeah, it's more about the state, right, at which the rock is at the moment that you record your image.
Yeah.
The image is the image, but you still need
to it will stay. That's right. There is more acoustic emissions when approaching failure. So that's a good point.
Thank you.
Yeah, interesting point. Chris Johnson, go ahead.
Hi, good morning. Thanks, François. That was fantastic talk. So as you know, we've primarily used the acoustic emission data, and as Patrick asked, ultimately we want to be able to, learn more about what's happening in the earth and can we apply this to data. So I kind of wanted your thoughts on the experiments that we're using out of Chris's lab. I mean, we have repeat failures, as you said, so we're breaking asperities that then heal throughout the cycle, whereas you break an intact rock and then you're not able to repeat the experiment. Can you kind of just give your thoughts on what you might find different in how we could continue to evolve this as we look at more field data because of the primary differences of the way the stress is being transferred through the system, kind of what you just showed where you're hitting grain boundary, you're hitting the boundaries for the fractures, but we have a little bit different scenario in the earth on active faults because primarily we're breaking regions that have already ruptured. So just kind of get your thoughts on that.
So for me, I was inspired by this, and that's also one of the reasons I make experiments where I break sample, is that that's right, if you look at California, most earthquake above magnitude 4.5, they are on the fault. But there is a lot of damage in the volume around.
Right.
So there are different ways. Either we break rocks to see how it will localize to the final fault. The other way would be to use a rough fault, so very rough fault, such that part of the volume around the fault plane is activated and there is some damage accumulating. And that is done now in some experiments. At the GFZ group, there is a nice paper published a couple of months ago where it was done. So what I don't say skeptical, but when you use only like flat interface and friction experiment, it simplifies a lot the rupture process, and the contribution of the volume is minimum. Everything is confined to the fault plane if it contains a gouge or even a bit of roughness. So all the complexity and the stress distribution occurs in a small volume in a 2D geometry. In nature, it's a bit more complicated. So it's how can we make experiment that will find a balance between the two, between exactly what happens on the fault plane to the damage zone and to the rock volume around. So that was the motivation of doing. I think it still works to do these rupture experiments for this reason.
Thanks.
I didn't show that, but we now do friction experiment as well. We use a sawcat and we slide, and we look at the deformation.
Chris? Yeah,
Yeah, thank you.
cool. Yeah, François, I have my hand up. I'll just ask a quick question. And start by saying, yes, a great talk, really a lot of interesting stuff. And I totally agree with you about, yeah, the value of having an experiment that images, you know, the deformation in 3D and really accounts for all the complexity of it. I wondered, you know, you compared in several cases different models, and you talked about fracture density. Can you say a little bit more about specifically how you measured fracture density, and if there were some things that you could do with fracture density by measuring more than just, I don't know, let's say is it like the centroid of the fracture that you measure when you talk about density? If the fracture has some length to it and one end of the fracture is close to another fracture, then I can kind of picture the density could be more complicated than just one number.
Yeah, so my term was misleading. It's fracture porosity. So what I call fracture density is the number of black pixels divided by the surface area of the image. So that would be the porosity. So what I call fracture density, it's a bulk property. In an image, in the 3D image like that, it would be all the blue volume divided by the volume of the cylinder, so the porosity. And the question I was asking is, because that's a bit intuitive, if there is more and more microfractures, the sample is closer to failure.
Yeah, right, I see.
So that's what we see in the deep learning. It's just that only the density of fracture on an image like that, so the volume of this, the surface area of this black fracture, is not as a good predictor as the image itself, because the image contains information about the orientation of these fractures, the distance between the fractures. So the internal organization, the spatial organization of the fracture is used by the deep learning model to make the prediction, which is better than just the fracture porosity.
Yeah, sure, totally makes sense. Yeah, I guess, is there a parameter that would help you measure localization?
What do you mean local orientation?
No, localization. Like is there...
Localization. That's another. So in this experiment, there is a very simple parameter that we use. Jessica Madbeck is using that a lot. Is to see where in a volume like that. No. So we don't use this. We could use the data. We use the 3D image correlation, and I will show you here. So we use 3D image correlation, and here we measure the volume of the sample occupied by the 10% largest strain value.
I see.
So here, the 10% largest strain value, they are very distributed everywhere, you see? So the entire sample, but here they start to be localized. So that's one way we use. And the other way we use is to look at the Gini coefficient. I don't know if you have heard about the Gini coefficient. It's a coefficient used in economy to measure the difference between, or the equality in a country. What is the difference between the rich and the poor? If you have a big Gini number, you have a lot of difference between rich and poor people. If you have a small Gini coefficient, you have a small difference. And that's a way also to measure this. you see that it's here. It means that all the strains go to a small number of individuals, or a small number of locations compared here where the strain is distributed. So we measure localization like that, either as a whole volume or through this Gini coefficient.
Yeah, very cool. I'll apologize because my internet connection is not very good, so I don't know if what I'm doing, but yeah, thank you very much. Alex Chubnau, go ahead, please.
Thank you. Thank you very much, François. It was an amazing talk. I have two questions. One you might have actually already answered, but I might have missed it. So I guess your prediction to failure, I mean, you have this correlation of 0.5 or 0.56, but it also gets better as you approach failure. So you didn't talk about the temporal, or I missed it, about the temporal evolution of your prediction in the cycle.
So first, I didn't look at that, but that's a good point. I should have looked at it.
Okay. Because the closer you to the failure, you think the better your prediction should become.
No, because you measure a residual between the true and the predicted value, and you average over. But that's more or less, if I feed the deep neural network with image like that, for each image, I can predict the distance to failure, and I get a stress strain curve like that. So that would be the stress and the axial strain. So that's the true data, and that's what I get. And so failure occur here at the end of the curve.
Okay,
so I didn't do the exercise, but I don't think the spread of the data varies significantly between far from failure to close to failure. There is some spread. It's not clear to me if there is more spread close to failure. But just remember also that what happened to failure, and that's another issue, is that the final failure is like a catastrophic event. So you have this power law increase of all correlations in the system. And this catastrophic event is quite fast. And predicting a catastrophic event within 1 or 2%, it's not that easy. So I think this last percent of the distance to failure, it's still, even with this data, it will be challenging to predict. And that's why I have residuals of the order of 1 or 2%. That's a residual. So I can predict the distance to failure within some percent, even close to failure.
Okay, thank you. Well, there are many people asking questions, so I will leave it there. Thank you so much, François. So
You can always come back, Alex, but yes, keep moving. Garrett Grayson, please.
Yeah, François, great talk, great stuff that you do. Now, I have a technical question. You may have answered this and I missed it, but when you were talking about measuring the length of the cracks, is that when you fit an ellipsoid to the extended pores, and then you define the long axis, and then you define the orientation of that long axis with respect to the loading direction, or how do I?
You have a fracture that is isolated, and we fit an ellipsoid. So from the ellipsoid, we get the 3 main axes.
Okay, so the fracture that you call a fracture is just a pore, right?
It's what you would call an elongated pore,
Yeah, okay.
Knowing that we start with sample, we don't have porosity. So at the beginning, there is almost 0% porosity. And then we have all
these inclined pores that you see are actually not single fractures. They are a combination of fractures that sort of coalesce, right? And you go back to this this scan that you showed, you couldn't see any or almost no inclined fractures. They were all tensile fractures in the direction of the loading.
It's not clear. It's not clear because if I go here, look at this one. I will remove the arrow. You look at this one, you see?
Yeah.
Some, they start to make an angle. So some of them, they are mixed mode. They are tensile, but with a shear component. So they open, but there is a bit of shear.
I'm not disputing that they are there, but I think that they actually form from a coalescence of many fractures.
Perhaps, yeah.
Yeah?
Yeah.
Okay.
At some stage, they will, when they nucleate, probably they are tensile, and then they will merge. But when they merge, it's a new fracture that can have an angle here.
Okay.
And for me, that was interesting is that because I was a bit like you, I thought it was only tensile fractures.
Mm-hmm.
But the fact that it predicts Anderson theory of faulting here, it means that if I feed only the system with
Yeah.
vertical stripes, the distance to failure is not as good.
Mm-hmm.
The prediction is not good. So it means that having only tensile cracks is not a good prediction for the distance to failure. You need to have some angle in this system.
Mm-hmm. Okay. I have many questions, but we do this later. Thank you.
Renz, go ahead.
I'm sorry, but I don't hear you. Your micro is a bit...
No.
Now I don't hear you at all.
Yes, sorry, Renz, I don't hear you either.
He's gonna write on the chat, he said.
Okay, John, why don't you go ahead and we'll come back to it after he puts it in.
Okay, I guess that's John. Yeah, great talk. I was curious, I guess, the part of the sample where the rupture nucleates, presumably is closer to failure in the approach to failure than the rest of the sample, and there's some heterogeneity in other areas might not be even close to failure. Have you homed in on the area where it nucleates to see if the signs of impending rupture are clearer where it actually does nucleate?
So I would love to have this information, but I don't have it. And the reason is that in a sample like that, so to get a scan, it takes 1 minute. And the final failure, it's woof. So it goes very fast. We are talking about a propagation of kilometer per second. So I don't have this step. What I have is the last step before it's collapsed, and I have a cross sample. So I don't know exactly where everything has started. But for example, for this sample, you see there is this zone here that starts to connect in 3D, and that's probably this one that breaks at the end. But where in this zone it started probably somewhere at a point, and then it expanded vertically. I cannot see it. So this technique is not ultra fast. So I would love to have that. It's
a few sensors on the rock might give you the epicenter of the break, so it might be easy to get that information.
Yeah, we can do. So there is something I didn't do, for example, is to do numerical simulation and to see where there is the highest stress concentration, because that would be the obvious place where it would start. Yeah.
All right, thanks.
Yeah, interesting point. Okay, and we're Renz, when you put the question in the chat, we can talk about it. But in the meantime, yeah, John, go ahead.
You mean me, right? François, I had a question about the slide that you were talking about when, but not the last question, but the one before. It was, showing the work you did with Joachim, where you take 2D slices, and I guess I'm wondering, why do you take 2D slices and not 3D slices? Like, is there some reason to organize it that way? Because I feel like the porosity has a 3D structure. So is that?
So there are two reasons. First, the number of samples. I have 8 samples. 50 scans each, a bit less, even 20 scans perhaps. So a sample for 20 scans, 160 samples doing machine learning is not obvious with so few samples. And the second one is that we are just using a normal computer, and loading the 3D data in a normal computer, it just feeds all the memory. So it takes ages it could take ages. It should be possible. So we consider, for example, slicing a sample like that in smaller subvolume. So feeding the neural network with subvolumes instead of feeding with 2D images. We found that 2D images, it was the best compromise between the time it takes to train and the data we had.
What You were just training it on a desktop with a graphics card?
No, it's a bit more than a desktop. It's a small cluster at Niels Bohr Institute,
Oh, okay.
but it's a cluster. It's not something bigger.
Yeah.
It's a GPU cluster.
Oh, okay. Well, then that kind of answers all of my questions, I think, because it's like it's a technological issue, not a. There's nothing to overcome except we need more money.
Everyone needs more money,
Yeah, that's
even
that's
François.
the goal.
Alex, you now go ahead.
Yes, thank you. So it's me again. So my second question actually was, so in the last part of the talk, you show how you perform the machine learning performs when you show him, you train him on seven on seven rocks and then apply it to an eighth one. And so I was wondering, have you looked at, you know, I mean, is my question is whether the prediction is lithology specific. So for example, if you train it on one data set of Carrara marble, do you get Carrara marble? Or do you need to have a training for every lithology, basically? Or is there like some sort of generic features, etc.?
So I think if I can make 50 experiments with 5 different lithologies, we will put in the deep learning the lithology. So can we predict the lithology?
Okay.
But we need that. We need 5 to 10 samples in each lithology. We didn't try because, for example, Carrara marble, we have 2. So if you use one to predict the other, it's a bit too small. But that's something I like to do, yeah, is to have a prediction of can we predict the lithology from the fracture pattern? That would be really cool, yeah.
And so then my follow-up, very quickly, sorry, is whether like when the eighth sample is a lithology you didn't have in the 7 first, is your prediction as accurate or is it lower?
So we didn't do that because we have at least 2 samples per lithology.
Okay.
So we don't have a sample which was the only one of his family.
Okay.
And we didn't want to reduce the number of samples on the training because it's 8 sample is not 8 rock is not already a lot, so we don't want to say too much. But there is something interesting, for example, is that there is a sample which we don't predict, which the prediction is very bad, and it gives a hint to. You see this one, Granite 2, more or less single, double convolutional network. It doesn't predict as good. It's like the null model. And if you look at this sample, it's this one. It's the sample for which we have only 5 scans. So this sample has much less data, and the result is that we predict it much worse because of this effect.
François,
So, yeah.
I wanted to point out, because I think one answer to the question also is a paper that we wrote with Jess a few years ago where we trained models on one rock type and then predicted them on another rock type.
Yes, we did some transfer learning.
Where it was like
it was not great. It was nice, but it was
yeah, it didn't it really demonstrated that there's more there is a geo in geophysics.
Yeah. That's this one, I think.
Yeah.
So we tried, Alex, but still we didn't have that many data to do this. And I see there is a question in the chat.
Yeah, Alex, are you okay? We move
Thank
on?
you, perfect. Thank you so much.
Yeah, okay, so let's go to that, and then we'll go to Vikram. Maybe you already read it, François, but I read it, and
I read it. I think it's a very good point.
okay.
It's when we look at features.
Yeah, particularly the SHAP value and like how.
Yeah,
does
the
that-
SHAP value.
Right.
So so we didn't try. So I think we can try. It's just that we train our machine learning model with all the data we have. And if we start now to separate them in time, so to train and to see how some value will evolve with time. What I fear is that we will have to train it with much less data. So we will degrade probably this R2 value, which is in this case was nice, but not really great. So I have to think a bit more. But it's a very good point. Is do this feature importance vary in time? One way to do it also would be also perhaps just to look at the two parts of the curve, below yielding and above yielding, for example, to see if the damage is different and evolve with time. That would be a way to look at, but that's a very good idea. I got many questions on the time, prediction in time, and see if parameters evolve with time. That's a good point.
Renz, thanks for putting that in there. And I'll just say, out loud to Renz and other people that, a lot of what can happen is to continue a conversation throughout the week by email or in other ways. So I'm sure François won't mind responding to an email or two. Vikram, go ahead.
Yeah, thanks for the nice talk. Very thought-provoking. I was just wondering if I understood clearly, the porosity and the fractures are having under the same threshold value for like marking, and if that's so, I can see that you have 8 number of experiments, and if this is the case, do you have the same threshold that you have used for identifying the fracture phase from the material phase?
Yes.
And
so what we do here, we start with a sample that has very little porosity. So that would be probably this. That's very far to failure. This one would be the initial porosity. And that would be the sample close to failure where the new porosity is fractures. So we did two things. Either we kept this porosity in the training and in all the process, or we removed this one. And the way we did that, we removed all the pores which had the shape close to a sphere. When every pore we had a shape close to a sphere, we say, okay, that's a pore, that's not a fracture, and we throw it away. And we do again the process. It didn't change the result much. And the reason is that these 8 rocks, and that's why we have chosen them, the initial porosity is very low. It's between 0.1 to 0.5%. So this initial porosity, which has the same gray value as the fracture, so when we extract it, it is there. In all the story I told you, it doesn't have an effect. So it's there, okay. But if we use it or if we don't use it, it doesn't change our prediction of the proximity to failure.
Just a quick follow-up with the, as you mentioned, Gini coefficient in this context. Like if you have like a high porosity rock, and if you apply that Gini coefficient, do you do during the testing of the data, or do you need to do some pre-processing before running your the deep algorithms?
So then you face the difficulty we have in high porosity rock. So I will show you a high porosity rock. This one is the high porosity rock. So all the blue is the porosity. That's a sandstone, 15% porosity. And in the porosity, some fracture develop. And the question is, can we separate the fractures from the pores? So in this case, we were lucky because they have a different grayscale, so we could do it. Otherwise, it's challenging because how do you define a Gini coefficient? If you just look at the porosity, there is porosity everywhere. And even during the fracture, it will not change much. So the Gini coefficient in this kind of rock, we have to find a clever way to look at it because it is strongly influenced by the original distribution of the porosity.
Thank you. Thank you very much.
Ian Main, go ahead.
Hi, just like everybody else said, François, that was a great talk. Really interesting, and the way you built it up from the statistical models to the higher levels of machine learning. I've got a question though on the filters that you use distribution. Did you design them, or are they kind of some basis functions that come out, from the analysis of the data? Or you're looking at different attributes in those filters, and how did you come up with them?
So they are built by the
I guess
model.
they're filters and spatial frequencies. They're produced by the model. Okay.
Yeah. So they are produced, that's the final filters. So there are 64 of them that are produced by feeding the model with 40,000 images.
Right. And are they in spatial frequency then, if they're a filter? Are they
No,
picking
they
up
start, it starts with a speckle noise, the filters. So they start with noise and they are built with they are built when we train the model. And at the end, we select the 8 which are activated the most by the stripe pattern, by this pattern. And that's is8. So it's difficult to see if there is any pattern here.
Yeah.
So for example, this one, you see there is some horizontal stripes. So this one is the most obvious. I don't know if you see the...
Yeah. And what would the horizontal stripes represent?
I don't know.
Are
It's
they
difficult.
closing fractures, or?
It's difficult because
action or something,
yeah, this model doesn't know there is fractures. It just see images.
Yeah.
And even so, this one, it was the most obvious analogy to make with the stripes because there are stripes and they have an angle. But the other one, it's you see this one and this one, they have some horizontal. I don't know.
Yeah.
Sometimes we say that this deep learning, it's a black box. So we are inside a black box here, and trying to make sense of this black box is I am careful.
Yeah, but still, it sort of shows how it's thinking in a strange sort of way. But it's obviously picking up these long-range correlations in the orientation distribution, which is, going back to Georg's question about how fractures link up. They're not growing in that orientation; they're kind of coalescing. And that happens before the time it fails. Like it's part of the process of finding the optimum in some free energy function or whatever to break the rock. Very, very.
But that's what perhaps the model is seeing is that you see this. If you look at this, can I put? You see, this one is perhaps a series of mode 1 crack that have the line. And the image now you start to see this angle around 20 degrees that appear. And that's probably signal that this linkage process has occurred to create this 20 degrees direction, and that the sample is closer to failure. That's something that the machine learning model has learned, is that when probably
it's finding those kind of aligned sets of fractures which are, it may be connected in 3D. That's another question, is the 2D, 3D thing, like whether that's contiguous in 3D, but it's actually on echelon in 2D.
But somehow the information in 3D is present because from this sample we take 2 images, but then we can rotate these 2 images a bit an angle like 10 degrees, 10 degrees, 10 degrees. So at the end, the 3D information of this sample will be present in a series of images. It's just that the 3D information is present in a series of 2D images.
But it is interesting that it knows there's long-range correlations in the data. It's picking that up.
I'm not sure it loses it because the filter is difficult to interpret these filters.
Yeah, okay.
It's
understand.
it's like in your brain you have neurons, but you still have a long-term memory, and so I don't know exactly how to interpret that. It was just for me, I find that as a curiosity, but I don't provide a causality. I don't want to provide a causal explanation.
Okay.
It's an interesting point, Ian, because you say long range correlation. It's at least big or long in comparison to the fracture lengths that are growing, right? It's multi-grain connections.
Yeah, but that's also what we see in the experiments where we slowed, the François showed some of the results from that, where we slowed down deformation, like in Dave Lochner's experiment. That shear band was there before the deformation localized very strongly along that whole shear band. So the nucleation that Dave Lochner saw happens after there's already a long-range kind of shear band structure. and then it begins to nucleate a zone of high strain, which then grows, as in his experimental results with the acoustic emissions. So that thing there on the left, when we did this, there was already a shear band going across the sample. And then you got the localization of strain on, a small patch, which kind of grows through the test. So, these long range correlations are there. It decides that pretty early, in between two snapshots, and then the strain localizes and grows along. So I don't know how it does it really, but it's finding this optimum angle pretty early,
So that's something we are working on. We look at how the localization occur in this part of the curve.
Yeah.
Before it reaches the plateau and there is a weakening, because the weakening is really when there is almost a screw going shear zone.
Yeah.
And localizations in our case start here.
Yeah.
And we look, for example, how the local dilation localize, how the shear component of strain localize, how the local compaction localize.
Mm-hmm.
And but even in this part of the curve, which looks like linear, some localization starts.
Yeah. It's a mixture of sort of hardening and softening processes, I think.
Yeah.
What looks like linear elastic is linear, but it's not elastic. You do have damage, you've got compensating cracks closing and opening, and somehow that averages out, or I don't know how to express it more scientifically, but it's certainly not elastic. It's not going to be recoverable in that, if you take the stress off, you're still going to have the damage.
And you see that in the acoustic emission, you start some activity here.
Exactly.
It's still in the elastic part.
It's just that the strain from is small, So you've got these two maybe competing processes, and you add them up, and they produce the apparent linear response in the rheology.
I think we've reached a point now where we shouldn't press François anymore. We should thank him for his time. Appreciate how much effort.
Thank you, Chris, for the invitation, and thank you for all the questions. It was really nice to have so many questions.